This is not as a complete lecture as I'd like to give because, as I mentioned, having been to Paris and to Grenoble twice in the last 4 days, I didn't get enough time to finish what I had to write here, so I'll have to add to this one in future years. Oh, damn, hang on. Speaking of Windows 10, my mouse has decided not to work, so I've got to go the keyboard. So I wanted to just put inequality in a bit of a perspective because, of course, that's become a major discussion topic politically and economically. Have any of you seen the talk about Piketty's book on inequality called Capital in the 21st century? So, and now conventional economists are admitting that inequality actually is an issue. But I wanted to put it in a bit of perspective because inequality in income and inequality in wealth is just, in one sense, is another form of variation between individuals. And people vary in everything, height, weight, intelligence, and largely speaking, those things, we don't complain about a difference in height between people. Some people might whinge about being shorter than they'd like to be, or maybe in some cases taller, but that doesn't cause many problems. When you get to talk about wealth and income and power, then we start getting issues about it. And it's partly, when I put this in context, it's partly because of the nature of the differences between those two categories. Because if you take a look at things like individual features like height, for example, your height doesn't depend on somebody else's height. Okay? Unless you're standing on somebody's shoulders, you're as tall as you are because of your own genetics. It's got nothing to do with how tall somebody else's genetics might make them a lot taller or a lot shorter. And when you look at it, and I'll try to give an explanation, a conceptual explanation of why this happens, what you get then fits what's called the normal distribution. Now, this is one of the cases where statisticians, I think, have made a similar sort of mistake that economists make. They hypothesize that things are natural or normal on the basis of a set of mathematical rules. So they talk about this. They call it the normal distribution because they thought that's the normal way things are distributed. Okay? It's like economists say there's a natural rate of unemployment, as if there's a natural rate the economy tends to, which I think is a total bastardisation of language. But statisticians did a similar thing here because when you look at things like the height that people have, then it's clustered around an average height. Most people are of average height. You could get a situation where there's an average that virtually nobody is. If you imagine a distribution where everybody was very short or very tall, okay? The average would be in the middle, but almost nobody would be there. So the normal distribution, the average is also the norm that most people have. And you also have this phenomenon that there's a very small number of extremely tall or extremely short people. We notice them, okay, because they do stand out, but there's a vanishingly small number of them in the overall population. You look at the social situation, things like inequality of wealth, then your income and your wealth does depend on other people's wealth, and I'll show you why in a fairly simple way in a moment. And therefore, what you get out of this is a variation called what's called a power law. Now, that's another intriguing. It's used because the word power is used there because it involves a mathematical power. You raise something to a power, like x squared is raised to the power of 2. Well, this is it's a power exponent turns up in the probability of something being larger than a certain level. That's where the idea of power law comes from. But it also makes a certain amount of sense when we look at it because it does relate to economic power, but even relates to the power of earthquakes, and I'll show you that in a moment. And when you get that, what you get is a dramatic variation of wealth. It's very, very hard to talk about the average wealth of someone. Okay, and trying to find somebody who's of average wealth it's a trivial exercise. Okay, you heard the old joke about an island which had an average wealth level of $500,000 per year, and they were surprised when 50% of the population died. And the argument was, well, it's because one person was earning $1 million, another person was earning nothing. The person earning nothing starves to death. So the average in that case tells you nothing about the nature of society. And what you can get when you look at power laws is you get many people can be very poor, but a few are very, very rich. But it's a larger number of few than it is in terms of very, very few people being extremely tall. Okay. You ever seen anybody who's more than 2 metres tall? There's actually one guy in our student body here who's 2 metres tall. Okay. I was walking with him through the corridors at Kingston. He had to duck to get below one of the door jams. Okay. So it does happen. Anybody who seems to be 3 metres tall? There is nobody. I'm not sure what the record is, because I think it's about 2.6, 2.7 metres is the tallest human's ever been recorded. Well, you think about your wealth and average wealth. If Bill Gates walked through the door with you, and you actually try to translate his wealth into a height distribution, he would be 20 or 30 metres tall. Okay? So it's something where there's much, much larger variation than we see in terms of things like height. So if you look at my favourite example here, because there's so many statistics on it, is the height of the American males. And the average male in America is actually, I'm precisely the height of an average American male, 175 centimetres, or 5'9" as I put it over there. And the standard deviation, meaning a measure of how much variation there is 7 centimetres roughly. So it means 68% of people are roughly between 165 and 185 centimetres, or more than about 70% of the population is there. And when you plot that, you get this classic thing called the bell curve. You all seen this in doing courses in statistics and maths and so on? So that's the common distribution of male height around that 69-inch average. I'm just putting it in a mathematical framework. That's the shape of the distribution. So on the bottom here I've got people who are 150 centimetres or shorter on that side. On this side, people are 2 metres or taller on the other, and you can see how rare 2 metres height is going to be in general. And here's the average, which is the 175 centimetres, and roughly 6% of the population is of that height. Okay? That's how many precisely that height. Then you say, well, how many are around it? Well, if you say plus or minus 7.1 centimetres, you get 68% of the population, roughly 2/3. And then if you go, oh, what about twice that, so 14 centimetres taller or shorter than the average, that's 95%. When you go out to 3 digits, that's 99.7%. That's, when you get past 4 standard deviations, there is virtually nobody. In 5 standard deviations, you get to the stage there's nobody who's that short or that tall, virtually on the planet. So that can mean in that simple little diagram you can cover a huge part of the variation that exists in terms of height. And another way to show this is look at the cumulative percentage. So I'm now taking how many people are less 150 centimetres tall or less, virtually zero. How many 155? A few. You get to 165, 170, you start getting 10% of the population there. Get up to 175%, you've got precisely half the population is shorter than 175 and precisely half is taller. And then you say, well, how many are 1 standard deviation more, which means about 183 centimetres. That's going to give you 82% of the population. And then with 190 centimetres, it's going to give you virtually 99% of the population. So 50% are shorter than the average, 50% are taller. 84% are shorter than 1 standard deviation above the average, which is about 183 centimetres there. And 97% are going to be shorter than 189.5 centimetres. Okay? So you're really capturing a huge part of the population just in that simple diagram. So how tall is somebody in the top 1%? You know, you've seen that slogan that David Graeber established about the 1% versus the 99 in terms of wealth. Okay. Well, if you look in terms of height, let's say we wanted to redistribute the height of the tallest person to everybody else. How tall is that person in the top 1%? Well, that's 191.8 centimetres tall. So somebody who's 2 metres, which is another standard deviation above that, is in the top 0.3%. Okay? No, 99.7% of the population is going to be below that height. So that's how rare 2 metres tall is. But to get the top 1%, you're talking about somebody who's 191.8 centimetres tall. Now let's say how much of the total height, imagine stacking everybody on top of each other, how much height does that the top 1% add of the whole thing? Well, what you look at is the height of the top person, and actually, if I've got 179, I would have to check those numbers. Let's see what I got there. I think I may have made an error there. Yeah, I have. Okay, so it'd be slightly taller, so it should be 190 something or other divided by 175. So 175.26 is the average. It's 100 people of that height. Literally 100 times that will give you precisely the total height of the population. You divide it by a slightly larger number that I'm showing there, so about you might get about 1.1%, okay, of the population being that height. So if you, and I'll fix it up when I put this up on the website. If you divide that, you find that the top person contributes maybe, let's say it's 2%. Could be that high, okay? Just to give an idea. So the top 1% has got 2% of the height, roughly. So if you then decided to make all the short people taller, you take the bottom half of the population and slice that person's height up and add it onto all the short people. How much taller do they get? Well, it's a fairly trivial amount. You'd add It's not quite. Maybe it'd be 3% if I did the maths properly. There, I'll fix it up, as I said, on the slides later. But it'd be a small improvement in the wealth, in the height of the average population. To take the height of the top 1%, distribute to the bottom half, you'd be making a fairly trivial change to the height of the bottom half. They might be an inch taller. That's it. So what you get in a normal distribution is whatever the attribute is, the top person's got a lot more of it than most people, but a small amount of the aggregate total. And therefore make any redistribution, and that is not going to have much impact. Why bother? Okay? A bit more detail on that just to go through in terms of the actual data in America. So the average is 178. Standard deviation is about 8 centimetres. You've got roughly 150 million people. So it should look something like this. And that's actually the data. That's the height of American males versus how many males there are of that height. So if you rank them now from the shortest to the tallest, and that's the pattern you get. And down here you're saying how many American males are below the height of 150 centimetres. You see it virtually disappears off the scale, virtually nobody. Then this flat region here, and then how many are taller than 2 metres, virtually nobody. Okay? That's the distribution when you have a normal distribution like that. So the vast majority, which is more than 120 out of 150 million, lie between 170 and 190 centimetres. So basketball players stand out because they are so incredibly rare. So incredibly small fraction of more than 2 metres tall, which is 2.75 standard deviations away, or shorter than 160, which is 2.25 below. So when you then say, well, let's now look the other way, what percentage of the population is taller than 140 centimetres? Well, virtually everybody is taller than that. Virtually everybody is taller than 150. Only you start getting 160 centimetres, you start getting a few people who are that height. Then you start getting, when you go past 180, then 60% of the population is taller than that. When you get to here, 200% of the population is shorter than 2 metres, pretty much. So another way again, that's not looking exactly the same data, but rather than looking at the heights down here, I'm looking at the standard deviations. Okay? So once you get past about 5 standard deviations, there's nobody. Okay? Well, that's you notice out here that's 4.5 standard deviations out here. You've been running along virtually the 100% line right from about 2.5. So you can almost forget about people who've only been more than 5 standard deviations above or below the mean. In fact, quite possibly there is nobody, period, on the planet out of 7 billion people who's that much larger or smaller than the average. Now, when you look at inequality of income and wealth, then it's much more unequal. And this is an interesting little chart I found in a fairly conventional academic paper recently, but still worth looking at. And that is saying that this one here tells you how much of the wealth do the top 10% of the population have. And you see, back in 1950 it was about 33%. It's now risen to 45, 46, 47%. So the top 10% have got 47% of the wealth. Now, the way this thing works is the next one down, which is S1, that tells you how much of this lot is held by the top 1%. So it's complicated to read, but I think the logic here is that the top 10% here are earning 45%. The top 1% earn 35% of that 45%. So they're getting roughly 15% of total income goes to the top 1%. So if you look at this, is like the total height. Top 1%'s got about maximum 2, more likely 1.5% of total height. Here, the top 1%'s got 15%, 10 times as much as you'd get if income was distributed the same way that height is. Okay? I'll fix those numbers up again, but that's the basic logic there. And notice that's risen from 33% back in the 1950s. And notice most of the rise began in the late 1980s. And if you think there's any potential link between Maggie Thatcher and Ronald Reagan getting to power and the whole deregulation and stuff, you may have a point. But it's more complex than just that. So I think there are 3 questions that arise out of looking at inequality of income in the context of inequality that we see in the world around us. One is, why is inequality of income and wealth so much greater than the inequality of individual characteristics? Is there too much inequality? And finally, why has it grown? Why has it grown so much since World War II? Those are the questions I want us to to look at here. And it's particularly since the mid-80s that that's happened. Now, you get many conflicting answers for the first question, and as usual, I'm going to say conventional economic theory is a useless guide. But it's a fairly simple reason as to why it is a useless guide. Because what they say is, well, individual differences in income reflect individual differences in ability. You know, the whole idea of marginal product. You know, somebody who's really wealthy has got a higher marginal product than somebody who's lower. And that's really saying it's all about the characteristics of the individual. So you get told that the reason Adele gets paid a fortune is she's got that much better a singing voice than anybody in this room. Anybody here got Adele albums? None. Great. I chose a dud for this particular audience. What's a popular singer for you? You got any music? Yeah. Okay. Yes. Anybody you can mention? How about you? Okay, well I chose Adele as my example here, but that's the basic explanation they give. Higher income means higher marginal product. That explains the whole thing. It's all about individual characteristics. Okay? But if that's the case, then why we've got things like height, aren't skewed dramatically. Even singing ability, to some extent, wouldn't be skewed. Well, maybe it is skewed dramatically. My voice is pretty dreadful. But is there something about the nature of where income and wealth comes from that's quite different to the nature of differences in individual characteristics? And this is where one of the areas that I work in I think is quite important, which is called complexity science. I've given you some introduction to that when I spoke about my Minsky model, but there's many ways we look at complexity, and one of those is called the network effect. And if you think about most people are workers, or they're sole contractors or unemployed. That would cover 80% of the population at least. And they're going to get income from one or at most a few other people. So if you're working, like I'm working at Kingston University, okay, well Kingston University pays most of my income, and most of my staff would only get their income from Kingston. I get mine from some other sources. But generally speaking, you just have one particular other entity which is providing you with income. And then when you look at where you pay out money to numerous other locations. So I pay for my rent, electricity, gas, train, transportation, food, etc., etc. There's lots of people that I'm linked to that I spend money on. There's more people, more organisations that I spend money on than give me income. And that's standard. So you buy from shops, you get, if you're your internet provider, train service, telephone system, etc., etc., all that sort of stuff. So what you have is lots and lots of very few income nodes. Most people have got one. Some people have got two or three. When you start looking at people who've got more than 4 or 5 other entities in which they receive income, then you're getting to a very tiny number of people. But there are lots of expenditure nodes, so you might have 20 or 30. If you actually sat down and tried to do a map of, and you could do it yourselves, who do I give money to? Categories, or even particular shops. How many different entities do I spend money on each month? There'd be quite a few. When you look at the very top, the bankers, industrialists, rock stars and stuff like that, they get income from many, many sources. Okay? Now when they spend, they pay to relatively few others. They probably spend more, they'd have more nodes than each of us would have, because none of us has a hairstylist travelling around with us in a jet all the time, so we don't have that particular expenditure. So their network of spending would be bigger than ours, but relatively few compared to the ones who pay them income. And consequently, what you get is they've got lots of income nodes and very few expenditure nodes. So even if there was just a standard amount of money passing from one node to another, they'd be much richer than you and I, okay? Just because of the number of entities that are providing money to them versus the number of entities they're providing money back to. So a network effect like that is going to give you a fairly strong explanation of why there's inequality, even if we don't go into other features about it, like the amount of money being paid and class structure and so on. So the rich are very strongly connected. They've got lots and lots of nodes that are bringing income into them. The poor are loosely connected, only a few little nodes that are going to bring money into them. So consequently, that alone is a good reason for why you're going to get income inequality. And if you had everybody being roughly as connected as everybody else, so there was no person like, we'd all be buying records off each other, rather than buying records off Adele or whoever you buy records off or MP3s off. That would be what's called a random network. But when you have a very structured network, so some people have lots of people paying to them and others have very, very few, you get what's called a scale-free network. Now, this language is a bit confusing. It doesn't mean there's no scale. Okay? What it means is it looks the same at every level. If you aggregate, say, rather than just looking at Adele versus the rest of us, you say, well, let's look at rock stars versus the rest of us. And you lump the rest of us into social classes or social groupings rather than individuals, then you still get it looks much, much the same. But that's the basic idea. A random network looks like this. You can see each person's got 2 connections here, roughly. Okay? Some people have got 3, but very, very few. Over here, this one person is connected to 6 others. This person is connected, and these 2 are connected through 2 others, and so on. So there's three groups, entities there that get many, many connections than the others have, and that's called scale-free. Get the basic idea? Now, what you get out of that is those different networks will give you different distributions of whatever you're looking at, whether that's income or wealth or earthquakes and things like that. So with a random network where there's no particular structure, no really concentrated nodes, you get the normal distribution, which is a bit like what we get out of height. Of course, that's not how height's determined, but that's that sort of phenomenon. If you find it, you're going to get a normal distribution of whatever the characteristic is that you're looking at. But if you have a scale-free network, then you get what's called a power law distribution, and that's where it's like income, where there's many people who are tens and thousands of times more than the average. Whereas in terms of height, of course, there's nobody who's even 3 times the average. And when you graph them and say, given a particular characteristics, what's the probability that somebody has that characteristic, then you get the normal distribution has this sort of shape, the power law distribution has this sort of shape, and I'll explain that in a bit of detail here. So if you look at income, and this is looking in America and Japan over the last, I could say 1999 is the year for these bits of data. What they're saying, here's the income of various people in dollars as of 1999. So people with 10 to the 0 means $1 income. Okay, virtually nobody. Hang on, so probability somebody's going to be up here. So we're actually reading that wrongly. That's everybody is up here has got an income of at least that much. How many people have got an income of 10 to the 4 there is $1,000 a year. Okay, so virtually everybody's earning more than $1,000 a year in America. Come to 10 to the 5, which is $10,000 a year, then you get 10 to the minus 1/10 of the population or so, or thereabouts, has got that much income. When you come up to 10 to the 6, which is 100,000, then 10 to the minus 4 of the population, which is 0.1%, has got that income. When you get out here, 10 to the 7, which is somebody earning $10 million a year, then 10 to the minus 6, that's 1 in 10 million, 1 in a million earning that much. And get out here, 10 to the minus 7, 10 to the minus 8, you're down to a tiny fraction of people who get it. But notice there's a straight line effect going here. Now, that's very different to the normal distribution, which has this sort of shape. It's not quite the same ways of rendering it, but if income followed the normal distribution, then this would be falling off down here. We get to the stage where there's almost nobody earning more than that amount of money. Okay? And I'll show you an example of that in a moment. Pardon?
Why did America stop?
Let's look at that again. Why does America stop? I think it's just bad data. It's incomplete. The Japanese data is more complete there. I don't know. That caught my eye as well. I've just grabbed that from somebody else's presentation. Normally what I'll do when I have time is I'll pull the stuff together myself, but this particular week just wasn't going to happen, I'm afraid. So I've cheated a bit for this league. This will be a better lecture next year. So let's look at some of the other phenomena that actually apply that same law. Now what's going on is, and this is something which I haven't told you properly, this scale here is using a log scale, 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, probability of a level. And this is whatever you're looking at, how often a word occurs in a book. What's the probability of a word being used? So when you plot a log against a log with this sort of distribution, you get a straight line. If you plot it with normal numbers against normal numbers, you get a really sharp curve. Okay? very, very tiny number of that particular characteristic, masses out here, that sort of thing. Again, I'll try to explain that more carefully later in the lecture. But this is showing, again, another one I've stolen from somebody else. That's the frequency of words being used in the book. The next one is the number of citations of an article, how many articles get cited in academic literature. The next one, how many hits occur on websites. Lots and lots of hits on Google, tiny number of hits on Kingston University by comparison. Books sold. Authors like J.K. Rowling are out here somewhere. Authors like me are back here somewhere. Telephone calls. Barack Obama probably gets a fair few. Earthquake magnitude, which is one I'll go into a bit more detail. How many earthquakes are there of a huge scale? Well, there's very few of a huge scale, but there's lots and lots and lots that are tiny. And the distribution follows a straight line when you plot the log of the number of earthquakes against the log of their magnitude. This is looking at craters in outer space. I'm not sure peak intensity applies to. Net worth in US dollars, frequency of names, population of cities. So all these things are quite common, important phenomena in society and in the universe, and we find that they follow this distribution. So in that sense, the true normal distribution may not be what we call the normal. It might be this power law thing. It's much more common than people realise. So if you look at the number of earthquakes, there's many, many, many small earthquakes. Anybody ever experienced an earthquake? What scale? Pardon? Every scale. Where do you come from? Pardon? Yeah. Which country are you from? Pardon? Afghanistan. Oh my God, well, you guys are world champions in earthquakes.
Yeah, I was there actually.
Yeah, what scale was the biggest?
The biggest was launched not launched, it's 2 months ago.
Yeah.
7.
8?
I don't know.
Something of huge scale. But has anybody experienced an earthquake of about scale 3 or 4? I've once experienced one. Australia has very, very few earthquakes. But I was working at my desk in Campbelltown, as it happens, which is a outer suburban place in Sydney, working away, and suddenly somebody jolts my chair and my computer turns off. And I turned around to see who was in the room, because it actually felt like somebody literally jolted me from behind. And the door was locked. I was the only person in the room, which is now dark, and I realised there must have been an earthquake, big enough magnitude to trip the power protection circuits in the local substation, and to make me feel somebody pushed me, just a little jolt. Now that's trivial compared to what you've experienced. Yeah, okay. But there's thousands and thousands of earthquakes of that scale, and you have to be right in the region where it happens to even know that it happened. Nobody, even 2 towns away, would have known that earthquake occurred. Okay? So there's thousands of those. There's very few at the scale you've experienced, but there's far more of them than if they were distributed normally, and that's the important point. So you get much, much more variation from power law than you get from a random variation. And the biggest is far bigger than the smallest. So if you plot the distribution, here's this idea again. This is the number of earthquakes per year of a certain magnitude. And notice that's 100, 1,000 going up here. And this is the log of the scale of them. So this is a particular region. I think this one comes from Southern California. So it's saying how many earthquakes of a Richter scale of 2, which is probably the scale of the one that I've experienced, about 100. So virtually one every 3 days. Okay? How many earthquakes of scale 3? 10. So about one every month. How many earthquakes of scale 4? 1. So once a year, that region would have an earthquake of scale 4. How many earthquakes of scale 5? About one every 10 years. And how many of scale 6? About one every 100 years. Okay, so you see the basic progression there? But the thing is, if you wait 1,000 years, down here you're going to get one of 7. Pardon? 9? Doesn't quite get that high. The Richter scale is actually a curious scale. It's actually to the power of 16. So each, like if you go from a 6 to a 7 is 16 times as powerful as a 6. And then an 8 is 16 times as powerful as a 7. So you've experienced 7. Okay. That's huge. I mean, literally everything.
I was sleeping.
Well, you weren't sleeping for long. Did you wake up? Yeah. A colleague of mine decades ago used to design earthquake-proof housing in Afghanistan. So we...
They make them.
Yeah. you've got to make it in such a way the structure actually is what Nassim Taleb calls anti-fragile. It's actually designed to take that shock and distribute it rather than collapsing around you. Pardon? Tsunami was a 9.2 or 9.3, and that's phenomenal. I mean, at some point, because the power law gets to the stage where you've got like an earthquake big enough to split the planet in two, you don't get out of that extreme end. It doesn't keep on going. But you can imagine the thing that wiped out the dinosaurs would have caused a pretty big earthquake, but it took another planet to bump into us or an asteroid to bump into us to cause that. So, but another little one, this is less dramatic, but size of cities. And normally, I do my animations from left to right. This is going to go from right to left. But this is the size of cities, population, and versus the rank of a city in terms of its size versus how large the city is. So, when you take a look at the log of the number of people in New York, when this chart was done, I'm actually amazed New York's at the top there. I would have expected Beijing. But that's got, Shanghai down here, and then you have Hong Kong, and then San Francisco here. Let's see what other names like them. St. Petersburg. I'm still trying to find some English ones there. London's got to be in there somewhere. But what you get is the same sort of thing applies with cities. So the size of communities we actually get involved in, again, follows this power law. That's how universal the whole thing is. And I'll go through the half hour, because I've only got about 1.5 hours, so I'll go straight on, by the way. I'm not going to stop at the 10-minute mark. But I thought it was useful just to look at the stock market here, because one thing, conventional economics gets so much wrong by thinking about things as if they're obeying this normal distribution that I showed you earlier. Okay? When in fact, when you look at the data, it follows this power law distribution. So when you look at the stock market, the red line is a plot of the actual movements in the daily movements in the I think that's the Dow Jones from 1915 to 2010. And you notice that we all know about the stock market crash back in the 1920s when it fell 13%, roughly 13% in one day, but it rose as much as 15% as well. So those are daily moves. And down here we had the 87 stock market crash when it fell 22% in one day. Okay, so that's the scale. The blue stuff is I've taken the average daily movement, which is about 0.02%, and I've taken the standard deviation of the average daily movement, which is about 1%, and I said, what would it look like if the data were random? Well, the blue thing is what it would look like if it's random. Okay? Now, conventional economics will teach you that that's the distribution the stock market follows. Couldn't be more wrong. But you only see it when you literally compare the data against what that prediction is. Now, that's a simulation as if it was normal. So I'm going to take that simulated data and say, what does it look like? If the simulated data was the real data, how can we understand it using some of the graphs I've shown you earlier? So I'm going to sort this from the biggest daily movements to the smallest daily movements to see what it looks like. And what you get is exactly the same pattern I've shown you for heights. Okay? There's looking at the percentage of daily movements that are greater than minus 4% or bigger than plus 4%, and there's none of them virtually. This disappears before you reach the four standard deviation or 4% movements. So, what's the actual data look like? And this is one of the dangers of the statistical techniques that economists tend to use as well. Have you heard of the concept of an outlier? Okay. Well, often you'll be told in statistical analysis, leave the outlier out. It's such an extreme event. It's not really going to happen very often, and it distorts the data, etc., etc. The outlier is the data. Okay? When you have a power law, there's no such thing as an outlier. Everything becomes an outlier in effect. But if you first look at it, you can actually think, well, it's not too different, because here's now looking at the actual data versus the simulated data. And looking at the two, if you decide to cut off the tails, it looks like you're not losing all that much. So you notice that you can just tell here that the simulated data cuts out before the actual data does. But there doesn't seem to be much difference down here. There is. Okay, but looking at it like that, you might think, oh, well, I'm just going to leave off the outliers and make it easier to analyse it, and then when I leave off the outliers, I get distribution, it looks like the normal distribution, and I use that to analyse and understand the stock market. Now, the question is, well, let's not do that. Let's actually look at the entire extent and say, if I now take this graph and go as far out in one direction and the other as the actual data does, what does it look like? So no limits on the horizontal axis, and I'm going to use the log with the percent scale rather than using, just because it's so hard to see, otherwise you can't actually see the vertical. And what you get looks like this. So your simulated data, which is the red line, has got far less variation than the actual data. So the actual data has got movements as large as minus 22%, which is way back here with the stock market crash, and up here plus 15. That's the actual data for the Dow Jones for the last century. So actually I do a bit more. Just now re-ranking the movements, now looking from the smallest to the biggest movement. So I've got rid of the actually no, it's a similar chart to the last one, but I'll just take hang on, I thought I had an animation. I know I've got an animation in some way. I stole this from an earlier presentation, as you can tell. Haven't fixed it up properly. Let's see. Okay, this is now looking at the percentage daily change. It's 25,000 trading days, so it's a fairly big sample of data. And what you get, and this is the part I hope I get the animations here. Let's see. Yeah, that's the range of the random walk. That's as much as it will tell you is going to happen. Okay? That's the actual data range. Far, far bigger. The random model tells you that there's only going to be one movement of minus 0.446, which is the maximum it actually generates. So they're saying how many times in a century we have the stock market falling by 4.5%, and the answer is once. Okay? How many times did it actually happen? 100 times. So that's how misleading it is to apply a random distribution or a normal distribution to the actual data. So it's very, very different to the Gaussian distribution, which is this normal distribution. And the maths behind it, I'm not going to, it's just to give you information to see where the idea comes from. So the number of events of a particular size is roughly equal to that size raised to some power. That's where the power law idea comes from. And the expression is like this: the number of events of size x is going to be roughly equal to x raised to the power of minus a, which just means 1 over x raised to that power. Now it looks a bit strange, but if you take logs of either side, you take the log of the number of events and the log of the scale, what you find is the log of the number of events is going to be minus alpha times the log of the size of that event, and that's where that straight line effect comes from. So you graph it and you find that relationship I've shown you so far. And of course it includes income and wealth. So in that sense, inequality is inevitable. If it comes out of the network effect, then it's inequality in income is as inevitable as earthquakes, because again, earthquakes are a network effect. We know that there's what we think is solid Earth is about up to 100 kilometres thick of crust above 3,000 kilometres of molten rock. Okay, and what's happening to the molten rock? It's like having a crust on a fat on a boiling stove, and then it will crack and move and float around and so on. And there's different elements there, different sizes that would move at different times. So a small part of the crust will move a small amount, or there might be a landslide underwater, that sort of thing. But other times, the whole plate on which Eurasia, like Asia and your part of the world, India and Afghanistan and Pakistan, are actually bumping up against the plate that holds Europe and Russia, etc., etc. And those two move against each other, and when they move, it's a gigantic scale of movement. So many, many more elements gets pushed around. So given that nature, that network effect is going to give you inequality in incomes, independent of differences in people's skills. So it's just an inevitable consequence of the fact that, I've chosen a bad example in this room, but many people of your age group will buy a record by Adele. Very, very few people are going to sell something to Adele. So consequently, the network effect for income far exceeds yours, and therefore she's going to be much wealthier, even without anything nasty about the inequality in that sense. It's just the fact that we interact with each other. So trying to get rid of it in that sense, if you try to get inequality at that level, you're going against the nature of interpersonal relations in a large society. But so the question is, are there any things making it more extreme than just the consequence of this network effect? That's what matters to me. Is something making it more extreme? And can it threaten the continued existence of society? And that, I think, is a real question. Now, there's no doubt that inequality has increased since World War II, and it's substantially risen since 1980, which is your age group. And the definitive study, this is done by a guy called Thomas Piketty in a book called Capital in the 21st Century. So I'm going to reproduce some charts from that now and give you an idea. So if you look at the inequality, this is looking at the percentage share that the top 10% gets in income between 1910 and 1920 for 4 countries. And you can see that over that time, from 1910 to virtually up to 1980, say for the UK, there was the top 10% got up to 45% back in 1910, 1920, fell down to about 35%, and by the 1970s they were only getting about 1/3. So the top 10% was 3 times the average in that sense back then. Now it's right back up to 45%, 40%, not as high as it was back in the days when England was an empire, okay, but still substantial. The American data is probably the most interesting because that's gone from being massively unequal, more unequal even than the Americans. Notice that peak there? Can you guess the year? 1929, stock market, okay? Stock market crash, Great Depression, World War II, at the end of that, all the way through the 50s to the 80s, no particular trend in inequality. And if you think about when conventional economic theory got really heavily developed by American academics, that was the period. So what they were perceiving when they were developing their theory was this period here. Very low inequality, and any variation in inequality you saw you might explain just using standard stats. Then from 1980 on, bang, back up here again. And now we're back at the level of inequality, which is as extreme, in fact in some cases more extreme. Notice that's the stock market crash in 2007. More extreme inequality than we saw back in the 1920s. And then looking in even more detail, this is saying, well, how much of that income is actually got by the top 0.1%. This is not the 10% or the 1%, it's 0.1%, so 1 in 1,000. Again, the same sort of story. The top 1,000 percent, let's take a look at the United States data, got up to 10% of the total income of the country back before the First World War, plunged during the First World War, rose during the bubble of the 1920s, the Roaring 20s, fell during the Great Depression, really fell during the Second World War, was very low from the 50s through to the 80s, and then took back off again, and it's now back up at the scale that it was back in 1929. So there is a pattern, there's been a change there, and the question is what's caused it. And of course rising wealth is a major factor. It's not people are earning more money so much that they've got more wealth which generates the income for them. So again, looking at the United States data, it's had a trend from 1970 of an increasing amount of wealth being held compared to GDP in those top countries. That's the wealth of the country divided by the GDP, and that's had a rising trend since 1970, and that's across all those countries. And capital gains are a major part of it. So if you look at the share of the top wage bill, the top percent in wages, then they get about 8. The top 1% got about 8% of the wage bill back in 1910. There's now up to about 12%. There's been a change in wages, but not a lot. It's when you look at capital gains that you get a dramatic change. Okay? So it's mainly driven by capital gains. So what could be driving that inequality, and could it be dangerous? Well, again, as I said, I wish I had more. I've actually spent the weekend working with people on this issue, with new papers that are actually based on some of my research, but I haven't had a time to incorporate it yet. But the basic points are that Piketty's explanation really doesn't cut it, because even though he's collected the data, which is a brilliant job and is very, very empirically oriented, when he thought about it, most of his explanations would have fitted inside a conventional neoclassical explanation where you explain everything on the basis of individual differences, not network effects. And Gael Giraud is covering most of that in his presentation. But the main one I want to focus upon is that the rising inequality is driven by rising private debt, and that's the work that Matheus Grasselli has done. So I've put both their presentations inside the slide on in PDF form. If you click on them, you can actually take a look at their presentations as they argued them. And the one I'm focusing on is Matheus's explanation, and it's a different angle on one that I found in my own work as well. And down the bottom he says here that when you have, if the economy is converging to an equilibrium where income shares weren't changing, then that'd be you're at a what he calls a good equilibrium in a dynamic model. But when you've got increasing income and wealth inequality, it's a sign that you're going to have a breakdown driven by debt. So it's a different analysis to how I explain mine, and I'll take you through mine now. Okay. So it's coming from the lecture I gave you in lecture 6 gives the mathematics behind the model, the basic logic. And if you think about income in, again, the model that I've built there, but also in general, you can say that total income in the economy is going to be the wages plus profits plus what bankers get, interest on debt. And if you put that into percentage terms, then you say the total in 100% of income is going to be either going to workers or profit share for capitalists or the income share for bankers. Those are the three social classes I'm putting there. And when I put the model together, what I found, and I'll explain this in more detail in a later course, I did a bit of this in lecture 6, but not enough. When I solved for the nature of this model, the profit share fluctuated near its equilibrium, not necessarily on. I'll explain that in a moment, but it fluctuated around it. So from the point of view of capitalists, not much was changing. Up and down, but no trend. But there's a direct negative relationship between what workers get, and workers are generally speaking poor, and what bankers get, and they're generally speaking rich. Pardon me, I should have been animated differently. So you get two possible outcomes. If you have an equilibrium applying, then wages share stabilises at a constant level, the employment rate stabilises, and the debt ratio stabilises, and there's no problem. But if the debt ratio continues rising, then capitalists continue getting much the same income share until the system collapses. And there's a rising bankers' share, which means the wealthy are getting more, and a falling workers' share, meaning the poor are getting less. And that ultimately leads to a situation where wages share collapses to zero, employment collapses to zero, and profit becomes negative. And that doesn't happen. What happens instead is society breaks down. You have things like the Great Depression or the Second World War coming out of it. So just to give you an idea of that, this is to simulate the model. If I've set up the model in such a way, I'll bring this up on the screen. Hang on. This is the simplest possible version of the model. So just to take you through it, I've got output. If you divide output by labour productivity, you get how many workers are employed. If you divide that by population, you get the employment rate. I've then got a workers' reaction to employment determining the wage rate. Wages times employment gives you the wages bill, and they can work out workers' share by dividing by output at that stage. Divide output by, if you subtract wages from output, you get profit, and that can give you a profit rate, which then I've got capitalist investing on the basis of the rate of profit. And if they invest more than profit, then they've got to borrow money for it, and they pay interest on the money for it, and they've got to pay that debt service, take it out of profit, and that gives you a banker's share. Now, I've just got down the bottom of this. I'm never sure how much is going to turn up on screen when I bring up one of these graphs, but let's just make that full scale. And then simulate this. And what you get, actually I've chosen the wrong, that's actually the level that leads to breakdown. I chose that wrongly. Hang on a second, I'll just stop this. Okay, go back to 0 again. If I set the model up so that you get converging to equilibrium, then you have these cycles in profit and wages and a rising amount going to debt, but ultimately it stabilises and you get permanent cycles coming out of it. So there's wages and profits are varying over time, but the debt level stabilises, there's no particular trend, and there's no breakdown going on there. Now, if I change the values so banks or capitalists borrow more money in response to a higher rate of profit than they did in the previous model, previous run. I'll slow this down a bit. Okay. Then those cycles appear to diminish for a while, as you can see. Then they start to get larger again. And finally what you get in the model is a total breakdown. Now it's a very stylized model, and it's also doesn't include variable prices and interest rates and stuff like that. So those are the two versions of the model there. When I go for a more general model and I include variable interest rates and stuff like that, then with that model you get a more realistic form of breakdown. I'm going to go downstairs and whereabouts are we? Find that graph. Okay. I hope that's turning up somewhere. Let's see. Hasn't yet. Oh, there it is. Okay. All right. I'll go back here. This is going to run slowly, I'm afraid. And this is a more realistic pattern of how things turn out. But you have worker share, which is the black line, appears to stabilise. The red line, which is capitalist share, is going to remain very, very close to that 20 line. You can see it on there. Cycles start to rise at one point, and then they appear to go away again, which might make you think the system's stable. But notice there's a bit of a trend starting to turn up in bankers' share. It's starting to rise, continues rising, and it's rising at the expense of the share going to workers, and now starting to go exponential. So worker share starts to plummet. Capitalists are still getting a constant amount. They're not seeing any problems. And finally, at the end of the whole thing, workers are now getting less and less of income. Bankers are getting more and more. And this society is going to collapse in a moment because profit level also starts to plunge. And you go into a Great Depression. This is a model of how a Great Depression comes about. So Grasselli's point, which is the same as the one that I've shown you here, is that if you have a rising trend of debt, that will cause more inequality, and the increase in inequality will lead to a social breakdown, because there's no way ultimately that people will accept that level of inequality. So you have a question. In that case, again, I'll do a better lecture when I have more time to write it for next year's class, so sorry getting a brief version here. But the basic argument that Piketty says, well, inequality is bad, given how extreme it's got to be, so we need to reduce it. And what he recommends is effectively bringing in progressive tax around the world and having agreements between countries to achieve that. Now, it's highly unlikely to achieve that for several reasons. First of all, the political power of the rich, which is going to oppose any change like that to begin with, and clearly bankers have got more influence on what the politicians are willing to pass than most of us have. But also, importantly, you've got to get international agreement. And there are some countries, and I'm singling out Ireland here, who exploited the fact that they charged lower tax to attract companies to their country. So it's really, really hard to get countries to agree to get rid of all that sort of stuff, because some of them are going to lose. And also, as we know, the tax laws, it's pretty easy to evade taxes if you're wealthy enough to be able to use all the various ruses that are available internationally. Now, the alternative proposal that I make, and I'll come and have a chat about this in the tutorial tomorrow, if you like, amongst other topics, what I call a modern debt jubilee. Because the whole problem is driven by too much debt. We need to find if we reduce the debt, we'd also reduce the inequality. And that's equally highly likely to be achieved, and for much the same reason, the political power of the rich, forget it. And also, I think the attitude the public has towards what the mechanism would be, which is they'd call money printing, and see that as being a way of leading to social breakdown when it's actually already happening. But if you could achieve it, then it would be almost impossible to get around. It's not like taxation where it's easy for the rich to evade it. This would be something where you're actually injecting something into the economy rather than trying to take money out of particular people, and it'd be very, very hard to block it. So the idea there is to use the central bank's capacity to create money, to put money directly into people's bank accounts, and that's a bit like what's been called people's quantitative easing, if you've seen some of the proposals that have come up around Corbyn recently. The only difference is I would require people who have debt to reduce their debt, and that's the extension to people's quantitative easing. And it's very easy to do right now because we all have bank accounts, and the bank accounts record whether we have assets, whether we have a cash or whether we have debt at the same time. So those not in debt would get a cash injection, those who have debt would have part of that debt cancelled, and that would reduce private debt without reducing aggregate demand, directly reduce inequality because you do it in a per capita way, but it also indirectly reduce it because if you reduce that debt ratio, and given the dynamics I've very quickly shown you there a moment ago, you'd also increase the amount going to workers via the dynamics of the overall system. It would ultimately end up being a higher wage share for workers, if not higher wages. And you'd also need to stop banks reproducing the whole thing by going back and lending again for housing bubbles, which is what they've been doing for the last 20 or 30 years. You need to find a way of encouraging banks to lend to businesses and entrepreneurs rather than to speculative asset bubbles, which is all they lend to right now.